Good day, everyone. Our topic for today is about bounds. These are upper and lower bounds. Now, when can we say that the set is bounded? The set is bounded if it is bounded above and bounded below. That is, the set has upper bounds and lower bounds. Now, what do we mean by upper bound and lower bound? Let me have this definition.
For any subset S of the set of real number, a real number U is an upper bound for S if U is greater than or equal to S for all elements of S. Now, a real number U sub 0 is the least upper bound or supremum of S if the two conditions are satisfied. First, U sub 0 is of course an upper bound, and it should be the smallest among all the upper bounds for S. We have here our notation for the least upper bound of S, or the supremum of S. Now, let me have this illustration. Let us consider the set or the real number line. Then, say for example, this is the set S. Now, for upper bounds for S, those values are greater than or equal to any element of S. So, we have here the upper bounds for S. So, these are the upper bounds. For S, and then for the least upper bound or the supremum of S, this is the smallest of all the upper bounds of S. So we denote that as U sub 0 in our definition, and this is the supremum of S. We note that the supremum of S is always less than or equal to the upper bound. So let us denote that as UP. Because the supremum of S is the least upper bound, so it should be less than or equal to all the upper bounds of S. So take note of this because we can use this one in proving some of the statements. Okay, for the lower bound of S, we let the subset S of R, and then a real number L is a lower bound for S if L is less than or equal to S for all elements of S. Then this real number L sub 0 is the greatest lower bound or the infimum of S if the two conditions are satisfied. First, L sub 0 must be a lower bound, and it should be the greatest among all the lower bounds for S. So we have here the notation for the greatest lower bound or the infimum of S. Okay, let me have this illustration again. The lower bounds for S are values that are less than or equal to S. So it should be here. These are the lower bounds for S. And for the greatest lower bound or the infimum of S, it is here. By the way, lower bounds here. Then for the greatest lower bound, we have this one. So in our notation, based on the definition we have L sub 0, this is the infimum of S. And note again that the infimum of S is always greater than or equal to the lower bound. because the infimum is the greatest among all the lower bounds of S. Okay, let me have this example. We let S sub 1 be the set. We have here the interval from 0 to 1/2. So to illustrate that one, let us consider this one, this real number line. Say for example, this is set from 0 to 1/2. Okay, the upper bounds for this set are these values to the right of 1/2. So the upper bounds are, we have 1/2 and the values greater than 1/2, or we can write that one as from 1/2 to positive infinity. And then for the lower bounds, this here, lower bounds are here to the left. So lower bounds therefore are values 0 and values less than 0, or we can write that as this one, including 0. So since this set S sub 1 has upper bounds or bounded above, and it also has lower bounds or bounded below, therefore this set is bounded. Now for the infimum of S, infimum is the greatest among all the lower bounds. So we have here the lower bounds. Greatest is 0, so this is the infimum of S. Then for the supremum of S, supremum is the least upper bound, smallest among all the upper bounds. So if we have here our upper bounds, the smallest is 1/2. So supremum of S is 1/2. So we have this one. Okay, lower bounds, upper bounds. Okay, let us try to consider this example here, the set of natural number. Now take note, for the set of natural number, we have this one. Okay, for the set of natural number, we have 1, 2, 3, and so on. Now take note, the upper bounds are values greater than or equal to the set. So for the set of real numbers, we know it is not bounded above, right? This is not bounded above, so there is no upper bound. And then for the lower bounds, of course, are the values here less than or equal to the set. So these are the values less than or equal to the set. We have the lower bounds 1 and all the values less than 1, or we can rewrite that one as this, including 1. So since this set has no upper bound, so this set is not bounded. It is only bounded below. Okay, is this one? So the set is not bounded. Another one is the set of integer. So for the set of integer, we know that the set of integer is not bounded above and bounded below. Therefore, there is no lower bound and upper bound. Therefore, therefore, the set is not bounded below and not bounded above. Okay, for this remark, we have the supremum of S and the infimum of S, if they exist, are not necessarily elements of S. Next, the infimum of S is less than or equal to the supremum of S if both exist. Then, why? Because the infimum of S, or S is in between the infimum of S and the supremum of S. So S is greater than or equal to the infimum of S, but less than or equal to the supremum of S for any element S in the set F. Okay, the third one is, if S is non-empty finite set, then the supremum of S is equal to the maximum of S, and the infimum of S is equal to the minimum of S. So let's have here an example. We let the set S sub 1 be equal to this interval, and the supremum is of course by the way, the upper bounds for S sub 1, as illustrated based on the illustration rather a while ago, are values equal to 5 and greater than 5. Therefore, the supremum is 5. Then, for the infimum, the lower bounds are values less than or equal to the elements in the set. So, the lower bounds are -1 and the values less than -1. Therefore, the greatest lower bound or the infimum of S sub 1 is -1. Now, as you noticed here, -1 is not an element of the set. So, therefore in the first remark, if the infimum exists, then it is not necessarily an element of S. Okay, for this example here, the second example, let us have here the set. Let's consider this set. Let's have this illustration rather. So this is 1. We have here 1/2. Next, 1/3 is somewhere here. Then 1/4, and so on. Notice that the elements of this set approaches to 0. So we have 0 here, but then we know that 0 is not included here. So for the upper bounds rather, upper bounds are elements greater than any element of the set. So we have here the upper bounds. We have from 1 to infinity. Therefore, the supremum of S sub 2 is equal to, that is the least among all the upper bounds, we have 1. Then for the lower bounds, of course, these are values rather less than any element of S sub 2. So we have here the lower bounds. So lower bounds are, we have this negative infinity to 0, negative infinity, and then 0 is included. So for the infimum of S sub 2 is equal to the greatest among all the lower bounds, we have 0. So the supremum, okay, S sub 1, this is in S sub 2. Is an element of S sub 2, whereas 0 is not an element of S sub 2. Now let us have proposition 1.10. Let A and B be subsets of R with A, subset of B. Suppose the supremum of A and the supremum of B exist. Then, the supremum of A is less than or equal to the supremum of B. So, in this illustration, say this is the set A, and the bigger set is the set B. This is B. Now, the supremum of B is somewhere here. This is the supremum of B, and this is the supremum of A. And as you can see in our illustration, the supremum of A is less than or equal. It could be equal if A is here. For the proof, let's have this one. Because the supremum of B exists as our assumption, we let that one as alpha as the supremum of B. Then by the definition of supremum, of course, it is greater than or equal to any elements in B. So we have here B is less than or equal to alpha for all B in set B. And then since A is a subset of B, so it is very clear that A is less than or equal to alpha. So if we let the supremum be equal to alpha, so the element A could be here or anywhere here. So as you can see, A is less than rather or equal to alpha, which is the supremum of B. Then alpha is of course the upper bound for A. Okay, because alpha is greater than any elements in A. Therefore, the supremum of A is less than or equal to alpha. Why? Because this alpha here is the upper bound for A. And we know that the upper bound is always greater than or equal to the supremum of A. So, upper bound, which is alpha, and this is equal to the supremum of A. So that's why we have the supremum of A is less than or equal to alpha. So we're done. We have shown that the supremum of A is less than or equal to the supremum of B. Now let us try to consider another proposition. Let A and B be subsets of R with A subset of E. Now suppose infimum of A and infimum of B exist. Then the infimum of A is greater than or equal to the infimum of B. So let's have this illustration. It's very obvious that the infimum of A is greater than the infimum of B. So say this is set A, and we have here bigger set, which is set B. So set B. And then for the infimum of A is somewhere here. So this is the infimum of A, and then this is now the infimum of B. And obviously, infimum of B is less than or equal to the infimum of A, or the infimum of A is greater than or equal to the infimum of B. Now for the proof, okay, we let the infimum of B is equal to beta, because in our assumption, the infimum of B exists, and we're going to show this one. So from the definition of infimum, since B is the infimum of B, so it should be smaller number than the number in the set B. So we have here beta is less than or equal to B for any element B in the set B. Since A is a subset of B, so we have beta is less than or equal to A. Okay, so since the infimum will let this as beta here, and the elements of A is somewhere here, say this one, so we know that beta is less than or equal to A. Next, in that case, beta is the lower bound. The lower bound for A. Because beta is less than any element in A. Now in this case, since the lower bound, beta is the lower bound for A, so this is less than or equal to the infimum of A. Because the infimum of A is the greatest among all the lower bounds for A. So we have here, this is beta, and our assumption is beta is equal to the infimum of B. So we have shown that the infimum of B is less than or equal to the infimum of A. So we're done. Okay, let's have the next one. We have here Theorem 1.2. So let S be a subset of the set R, and U is the supremum of S, where of course U is a real number. Now, if epsilon is greater than 0, then there exists an element of S such that S is greater than mu minus epsilon, but less than or equal to U. So we have this illustration. So we have set S here. This is set S. And then for epsilon greater than 0, say we have, by the way, this is our U. This is the supremum of S. So somewhere here. And then mu minus epsilon, because it is greater than 0. So let's have it here. Mu minus epsilon. So the distance here is epsilon. So as you can see here, because we have here u minus epsilon, there exists an element of S, say S, in which S is less than u minus epsilon, but rather S is greater than u minus epsilon, but less than or equal to u. And let's have here the proof. In our assumption, we let u be equal to the supremum of S, and epsilon is greater than 0. Then, of course, as you can see in the illustration, u minus epsilon is not an upper bound for S because u is the supremum of S. And we know that for the supremum of S, it should be the least upper bounds. So, list upper bound. So, this must not be an upper bound. So, dapat ang upper bound is somewhere here. So, u minus epsilon is not an upper bound. This implies that there exists an element S in the set S such that u minus epsilon is less than S. So, we're done. Let's have here another theorem. If we are going to let L be equal to the infimum of S, where L is a real number and epsilon is greater than 0, then there exists S in the set S such that S is less than L plus epsilon. So the concept is most likely the same, in which we have here, if we have the set S here, so L is somewhere here, which is the infimum of S. So this is the infimum of S. And then, for any epsilon greater than 0, we could have L plus epsilon here. So it could be closer to L. So for any epsilon greater than 0. And we're going to show that there exists an S such that S is less than L plus epsilon. For our proof, we have this one. So, by our assumption, L is equal to the infimum of S and epsilon is greater than 0, then L plus epsilon is not a lower bound for S. Now, as you can see, because L here is the infimum of S, and we know that the infimum of S is the greatest among all the lower bounds. So, lower bound should be here. So, L plus 1 is not a lower bound for S. This implies that there exists an element S here such that S is less than L plus epsilon. So, that's it, we're done. Okay, let's have theorem 1.14. We let any subset A of R and the negative of set A is equal to this set. First, a real number C is an upper bound for A if and only if negative C is a lower bound for negative of set A. Second, a real number RC is a lower bound for A if and only if the negative C is an upper bound for the negative of set A. So we will prove first number 1. Take note here that we have if and only if statement, the necessary and sufficient conditions, in which we are going to prove two statements here. First statement, the necessary, the assumption is for any real number C, which is an upper bound for A, then we will show that negative C is a lower bound for the negative of set A. And then for the sufficient condition, we let negative C as a lower bound for negative A. And then we will show this, that a real number C is an upper bound for set A. So let's do it. So we have this, the necessary condition. So it means we will assume that C is an upper bound for A. So here we suppose C is an upper bound for A. Then by the definition of an upper bound, of course, it is greater than any element in A. So we have this, A is less than or equal to C for any elements A in the set A. Hence, from this one, we have negative C is less than or equal to negative A for all A in set A. Therefore, negative C is a lower bound for negative A because negative A is in the negative of set A. Lower bound, it is less than any element in the negative set A. So let me have this illustration. Okay, so if we have here set A, so the negative of set A is somewhere here, the negative of set A. So if C daw is an upper bound for A, which is our necessary condition, if C is an upper bound, so say we have C here, C, which is an upper bound. This is an upper bound for A. So if we have C here, of course, negative C is somewhere here. So as you can see, negative C is this is the lower bound for negative A. Hello? Okay, so we're done proving the necessary condition. And for the sufficient condition, we have here, we are going to suppose that negative C is a lower bound for negative A. So we have this assumption. And then since it is a lower bound for negative A, so negative C is a lower bound, it means it is less than any element of negative A. So negative A is an element of negative of set A. So lower bound is less than, so for all element, or for all A in set A. And from this, we have this, A is less than or equal to C. Now as you can see, we have here element A in the set A, which is less than or equal to C. It means C is greater than, it means C is an upper bound for A. So we're done proving number 1, the if and only if statements. And then for the second statement, this will be your problem set number 1. So let's have the next theorem. We left here A, B, set A be a subset of a real number R. We have the negative of set A. First statement, if the supremum of A exists, then the infimum of the negative A exists. Moreover, the infimum of negative A is equal to the negative supremum of A. Then the second statement is, if the infimum of A exists, then the supremum of negative A exists. And supremum of negative A is equal to the negative infimum of A. Okay, to illustrate that one, okay, let me have this. Again, we have this real number line. So if we have set A here, this is the negative of A. And then if the supremum of A exists, so we have here, this is the supremum of A, then the infimum of negative a is here. So the infimum of negative a exists. So moreover, this is equal to the negative of the supremum of a. And the other statement is here, if the infimum, let me erase this. For number 2, the second statement, if the infimum thou of a, this is the infimum of a, exists, of course this is the supremum. So we have here the supremum of negative a exists, and then we are to show that this is equal to the infimum, negative infimum of a. So let's prove it. Let's have the first statement. So we suppose here that alpha is equal to the supremum of a. Why? Because in the condition, in this assumption rather, the supremum of a exists. So we can let any number. So we have alpha is equal to the supremum of a. So we want to show that the infimum of negative a exists. So this one exists. So by the definition of supremum, alpha is an upper bound because a supremum is also an upper bound for a. Hence, being an upper bound, alpha is greater than any element of set A. That's why we have this one. Then by the preceding theorem, number 1, states that if alpha is an upper bound for A, then the negative alpha is a lower bound for the negative A. So our claim now is, we want to show that this negative alpha here is the infimum of negative A. So since it is a lower bound, negative alpha is a lower bound for negative A, we only need to show that it is the greatest lower bound of negative A. So we have this one. Okay, we let beta is a lower bound for negative A. That is, being a lower bound for negative A, it is less than or equal to any element of negative A. So any element, we have here negative A for all negative A in the set, negative of A, or for all A in A. Now take note, we supposed here another lower bound beta for negative A because we want to show that this negative alpha here is the greatest lower bound. So that's why we suppose another lower bound. So we want to show that this is the greatest. Then this negative beta here by the preceding theorem, number 2, which states that if beta is a lower bound for negative A, then the negative beta is an upper bound for A. This means the supremum of A, which is equal to alpha here in our assumption, is less than or equal to negative beta. Why? This is because negative beta is an upper bound for A, and alpha is the supremum of A. Take note that the supremum of A is the least upper bound. It is smaller or equal to an upper bound for A. So that's why we have this. Hence, from here, we have beta is less than or equal to negative alpha. So we have shown that negative alpha is greater than beta. So this is now the greatest lower bound, because we have supposed that beta is a lower bound, and we have shown that negative alpha here is a lower bound also. And then it remains to show that negative alpha is the greatest lower bound to make it equal to the infimum of negative A. Therefore, the negative alpha, which is from our assumption, alpha equals supremum of A, therefore negative alpha is equal to the negative supremum of A, which is equal to the infimum of negative A, set A. So we're done. Now, number 2 is your problem set.